Okay, hello everyone. This is Salar, and we are in part 18 from our tutorial, a tutorial to writing a real-time operating system. But in this part, we're going to use an IDE for works, okay? IDE stands for Integrated Development Environment. So, as I said in previous part, we want to use a graphical software instead of terminal to do our project, compile our project, link our project, and debug our project. So in this part, I want to talk about an IDE. But what IDE we want to use? In this part, I want to talk about Eclipse. But why Eclipse? Because Eclipse is better than other IDEs for our works. Okay, and many of chip manufacturers make their IDE by Eclipse. For example, ST Microelectronic, Texas Instrument, NXP, Renaissance, Cypress, and other chip manufacturers. Okay, because Eclipse has a lot of facilities for our works. For example, for our programming and debugging. Okay, and we can do our works easier in Eclipse than terminal. But why didn't we start our work with an IDE? And we started our work by doing our programming and debugging in terminal. Because when you work in terminal and some tools like Makefile, you earn better understanding about these tools, compiling, debugging, and doing your works. Okay, so now we have a lot of information about compiling process, linking process, debugging, and writing our program for embedded system. Okay, now I want to introduce you Eclipse. So how can I download Eclipse? Let's do open my web browser and search for Eclipse IDE for embedded C and C++ developers. Okay, it's an IDE that dedicated for embedded C and C++ developers for some chips and computer architectures like ARM and RISC-V. Okay, search for that and go to Eclipse website. You can go to download tab and download Eclipse embedded CDT. Okay, for C and C++ developer. Okay, C and C++ development tools, CDT. You can download it for Windows, Mac OS, Linux, and ARM Linux. What's ARM Linux? Those computers that have Linux operating system, but its CPU is based on ARM processor, like Raspberry Pi. Okay, so you can download and install Eclipse for your Raspberry Pi. Okay, but from now you can follow this course in other operating system. What means? From now you can follow our works in all of operating system, Windows, Linux, because when we work with an IDE, or environment is similar in all of operating system. Okay, so if you have Windows, from this part you can follow my work. Okay, you can follow my tutorial in Windows operating system by installing and download and installing Eclipse IDE. Okay, you can download and install it and use it. But I've downloaded Eclipse IDE and I have Eclipse in my desktop. Shortcut of Eclipse in my desktop. Let's do open Eclipse. And double click that Eclipse IDE, the last version. Okay, when you see this dialog, you can select the workspace. What's workspace? A directory that Eclipse will save your project in that. Okay, so my workspace in home, Solar and Eclipse workspace. Okay, a directory in my home directory. Okay, now launch, press launch to launch Eclipse. Please wait to launching. Now, here is Eclipse, and in home directory, my home user directory, I have my workspace. Okay, here is Eclipse workspace, and all of my stuff will be saved here. Okay, here is Eclipse. So how can I create a project in Eclipse? To creating a project, go to File and New and C and C++ project. Create a new C or C++ project. In this dialog, you should use this option C managed build or C++ managed for C or C++. You can select other options, for example, Makefile, but when you select this option, Makefile project, you should write your Makefile by yourself. But when you select C managed build, Eclipse will create your Makefile automatically. Okay, so good, and it can make our work so easier. Okay, press next. Okay, in this dialog, you should set a name for your project. For example, first Eclipse. Okay, for my first project in Eclipse. And when you select this tick, it will create a directory with this name, first Eclipse, in your workspace. Okay, in project type, you should select empty project, because we want to do our work in Eclipse from scratch and from toolchain ARM cross GCC. Okay, a cross compiler for ARM, a GCC cross compiler for ARM processor. Okay, press next. In this dialog, you should select and check these two options, debug and release. But what's debug and release? What is debug and release? As you can see, for example, if I want to create a project that I can debug that, I should add -G to my options. Okay, but if I want to just create a project for Flash on my microcontroller, I should ignore -G option. So if you want to create a project for debug, you should have some other options. Okay, in this part, you say to Eclipse to create two types of options for your project, and we can config debug or release separately. Okay, I will talk about debug and release in this part. Press next. Give the name of your toolchain. My toolchain is from ARM. But what's Xpack? Xpack is just like ARM. Okay, there is no difference between Xpack package for ARM compiler and formal ARM compiler. But you can download Xpack from Xpack website. You can study about that. But there is no difference between the compiler that we have downloaded, but by this compiler. So after that, you should give the path of your toolchain tools, this path of your compiler, debugger, and other tools. Where is the path? In home, my compiler my compiler directory, GCC ARM, and binary directory, bin directory. You should give the path of this directory: home, Solar, GCC ARM, and binary directory, and press finish. And so after that, click on Window, and in Show View, click on Project Explorer. Okay, in Window, Show View, Project Explorer. Here is Project Explorer and file in my Explorer. As you can see, Eclipse automatically add your compiler include path to your project. Okay, it's some include path from your standard library from your compiler. Okay, but in this time I need to add some files to my project. Okay, I need to add some files in my project. As you can see here in home Eclipse workspace, I have a directory for my project. Open that. Here is my directory project. So I want to add some files in my project. You can add some files like your previous project in previous part. Let's to open previous project from previous part. It was first CMCs. Okay, I need to add main.c to my project. I need a main function. Okay, it's the code that we have compiled in previous part. Okay, after that you need to add CMC's core include. Okay, you need your include file in your directory. Copy include file and paste it in your project. Another is your device, your specific device. Why we should add my specific device, just RMC? Because when you create your project with Eclipse, Eclipse will compile all of C file and all of source file in your workspace. Okay, what's my workspace? Here, the directory of my project is my workspace. Okay, directory of my project is my workspace. So Eclipse will compile all of these files. For example, all of your source files. So I have a startup file in assembly code and a startup in C code. Eclipse will compile all of that and create some error because you have two startups. So I should delete one of the startup. So I should delete startup.c because I don't need that. But in previous part, when we create makefile, we just add assembly file in my project. But Eclipse will find all of your source file, compile those, and link to your project. So you should delete those files that you don't need. Delete this file and delete these two directories from yar and on because we don't need them anymore. Delete them. Okay, here is my project. In GCC, I have my linker script and startup, assembly startup. I have my system init file in this file. And I have my CMSIS header files and some header files from my device and some header files for CMSIS. Okay, we need these files in our project. So let's do other configuration to create and compile our project. Another time, open your Eclipse, right click on your project and refresh. Okay, I have added this file in this directory and file in my project. So when I want to compile my project, I should give some options to compiler like before about my core, about some define, for example -d and arm-cm7 and these options like before that I've added in makefile. So how can I add these options to my project? For that, right click on your project. Okay, in Project Explorer directory, on your project, right click and select properties. Select properties. In this dialog, go to C and C++ build and setting. It's an important part in creating project. Okay, and in this part I can have two configurations, one for debug and one for release. As you can see, two separate configurations, but in this time I want just config for debugging. Okay, just config for debugging. I can select my CPU in a graphical mode. Okay, it's so easier. Cortex M7. Okay, Cortex M7 is my processor, and leave other options unchanged. Okay, in another page in optimization, in optimization. In this time, you can uncheck all of these options, okay, because we don't need them. But in future parts, I will talk about all of them, okay? And it's optimization level. And I don't want to optimize my code, okay? So O-O0, it's a default. When we didn't add this option in our code in makefile, your compiler added the default value, and the default value is -O0. Okay, in a warning, leave all of options unchanged. And in debugging, set the debugging level G, -G, just -G, like in makefile and previous projects, and uncheck and leave other options unchanged. For your assembly, you can add some using preprocessor for your assembler. Okay, you can check or uncheck that, but it's not important in this part, and we can uncheck it because we don't need them in this part. Okay, and in include, you can add some path in your include for your assembly code, some warning, unchanged, and miscellaneous. Okay, leave it unchanged. But if you can see in for your assembly compiling, you have -X and assembler. What's that? You can add this option in your GCC and say to GCC that my file is assembly, but no, it's not a necessary option, because when GCC see your suffix, for example .s, it can recognize that your file is assembly, but you can add it. Okay, -X assembler, and this option in Eclipse is default. Okay, is a default option. But for compiling, okay, here for compiling, option for C compiler, compiling your C file. Okay, in preprocessor, we should add a preprocessor for compiling. What's that? A preprocessor that we have added in makefile. Name of our core, like makefile, ARM CM7. Okay, and Eclipse will add this option with -D in your compiling process. After that, we should include some path in our compiling process. What's path? We can add paths from our workspace, but you can add them from file system or workspace. Okay, file system is all of file in your computer, but workspace is your project directory, first CMSIS. From first CMSIS, add include CMSIS core include. Okay, and include your device header here. Okay, like in makefile. In optimization, you can change it to default. Okay, and change warning options unchanged. Leave warning options unchanged. And in miscellaneous, here you can, for example, run your compiling in verbose mode. Some options like this, and you can leave it unchanged. Okay, but for linking, ARM linker. Okay, C linker. In general, we can add our script file, linker script file to project from workspace, ARM CM7 source, GCC, and LD, GCC ARM LD, or linker script. Okay, and you can add some libraries, but we don't need to add libraries to our project in this time. And from miscellaneous, you can add an specs file to your project. Okay, like in makefile, and in this time you can delete this part. Okay, it's all about linker. But in general, It's better in this time, it's not important. You can uncheck this option. This option do garbage collection for your code. Okay, what's garbage collection? I will talk about that. But in this time, we don't need that and we can uncheck that. Okay, now we do all of configuration. Apply and close. Okay, apply and close. Press yes, and now we do all of configuration. But if you another time open your project properties, you can open your project properties from here, okay, from this list, or you can open that from Project Explorer. Right click and properties. You can do another configuration for release, okay, another configuration for release, but we don't need to do that in this time. In this time, we just do it for debug. Okay, here is my main file and it's my project, and in this time I want to compile my project. So how can I compile my project? You can click on hammer button, but before that select debug configuration, okay, because we don't do the configuration for release this time, just for debug. Okay, press hammer to compile your project, and if you press hammer, okay, we did that one time. How can I clean my project? Like a makefile, go to project and clean. Okay, select your project from Project Explorer, go to project and clean here, and uncheck this option, because when you check this option, Eclipse will create and will build your project after cleaning. But in this time I want just clean my project. Check this option and clean. Okay, now my project has been cleaned. Okay, my project has been cleaned. Okay, close console, and another time click on hammer button for building project. Okay, full screen console. In this time my project will create it. Okay, my project will create it. In this part it creates my it creates an object file from my source and from my assembly file, after from my system file, and after that from my main file, like in or makefile that we have written in previous parts. Okay, and at the end link all of my project and create an ELF file. Okay, create an ELF file. But you can see some options here, -m, md, -mp, and -mf. What's this option? This option is for automatic dependency generation. What's automatic dependency generation? As I said, in makefile parts, you can study about that. But when you do automatic dependency generation by makefile will find all of your header files and add them to your project. Okay, so as I said, it's so important to add your header files as a prerequisite to your makefile. Okay, but in this time Eclipse do it automatically. Okay, if I open Eclipse workspace, my project, in debug, for debug configuration, I have some makefile that Eclipse create automatically. So it's so easy. You can, if you are curious about that, you can open them and study them. Okay, you have some main.d file, and it's about automatic dependency generation, your ELF file and hex file. I will talk about that hex file and difference between ELF file and hex file in future parts. Okay, and some object file from your startup file. Okay, here is all of your project, and you create your project and your output file, your ELF file, is so easy. Okay, in this time I can flash my board and flash my chip with this ELF file. Okay, in debug with this ELF file. For that, let's do open terminal and do pyocd list. Okay, my board is connected to my computer, and in this time I can flash my board. pyocd flash and name of your ELF file. What's the name of my ELF file? First cmsys.elf. Okay, if I press enter, now my board has flashed. Okay, and you can see here the green LED on my board. Okay, you can see green LED on my board another time. So easy with Eclipse Id. But we have a lot of information about compiling process because we do our works in previous parts and with terminal. Okay, and we know what Eclipse does. Okay, it can create makefile and do our project. Okay, now how can I debug my project? If you want to debug your project, you can do some configuration for debugging in Eclipse. Okay, just like for compiling. Okay, just like for compiling. So how can we debug our project in Eclipse? For doing the configuration, go to run and open run configurations. Okay, in this dialog you can do your configuration, but I did my configuration here. Okay, let's delete that and another time do configurations. Select that and delete. Okay, delete. Another time you can do configuration for OpenOCD, a GDB server, PyOCD or GDB server, QEMU. QEMU is a simulator, okay, but we are using a real board and real microcontroller, and we don't need a simulator, okay, or for Seger J-Link, okay, but we want to debug our project with PyOCD. Right click on this PyOCD and new configuration. So here you can add a name for your configuration. For example, here I can write PyOCD, okay, and you can add the name of your project and the path to your ELF file in your workspace. In my workspace, directory project, debug, and first eclipse.elf, and it's the name of my project. Leave other option unchanged in tab, but in debugger tab, you should give the address to your GDB server. Where is my GDB server? To find your GDB server, you can you can run a command in your terminal, reach and pyocd-gdb server. What's pyocd GDB server? It's a GDB server from pyocd, like running pyocd and GDB or GDB server. Okay, it's just GDB server. Okay, and you can find the path to your GDB server. Okay, here is path to my GDB server, and you should add it here. Okay, after that you should give the port of your GDB server, like previous part 3333. But in this time, you can uncheck semi-host port, semi-hosting port. Okay, I will talk about semi-hosting port in next part. Okay, after that, you should plug your board to your computer. You should add the pack for your PyOCD and refresh to find your board, like here. Okay, here is my board, and PyOCD and Eclipse automatically find that. Okay, and in this part, Gdb Client Setup, you should give the path to your ARM debugger. Where is my ARM debugger? In home directory, my compiler directory, in bin directory here. Okay, here is my Gdb ARM debugger, and here is address to my debugger. And leave other option in this tab unchanged. And after that, in startup, when you open in your computer, this part is in it. Okay, this part is in it, but it's better, you should change it to default. Okay, it's one option from PyOCD. Type of your reset, what is it? Says that when run debugger in your code, first reset your board. But what's the type of reset? You can study about type of resets in PyOCD documentation. Okay, if you open PyOCD website in GitHub, the repository in GitHub, and in PyO documentation, and in command reference, you can search for reset and its types here. Okay, you can study about reset and its types here. So change it to default. Okay, change it to default. It's better to, not important, but in this time you can uncheck this option. You can unchange the option. It's not important. In this time you can unchange that. Okay, but you can leave it unchanged. It's not important. Let's leave it unchanged. Okay, it's in this time when you check this option, it loads your project when you debug your program, like or debugging in previous parts. Okay, and you should add another reset on your board with halt option, like before. Okay, like halt before starting your project, and adding a breakpoint to your main function, like in Gdb in terminal, and continue to your main function, like previous part. We did all of these works, and you know what this works. Okay, and in this time leave other tabs unchanged. Okay, apply that. First, let's wait to apply and run. Okay, and press run. Sometimes when you click run, Eclipse doesn't run your compiling. Eclipse has some problem with that. If your compiling doesn't start, right click in console here and press terminate. Okay, close console, and another time click on this button, ladybug. Okay, click on this button. Ladybug is an insect, and it's the button for debugging. Okay, here is the one configuration for debugging. Set that and press in this button. Okay, now I will go to debugging layout by clicking on switch. Okay, by clicking on switch. As you can see, my debugging has been run, and we are in line 6, first line in my main function. So easy. Okay, so easy, by just do some configuration. In this time I can do my debugging in a graphical environment. Okay, so how can I do debugging commands here? Okay, for example, one of commands is next. We have some button here. One of that is step over or F6 in keyboard, and it do next command in Gdb. Okay, go to next line. Here is a step into or F5 in keyboard. It's like a step command in Gdb, and it's if you have a function in your line, it will go to your function. Okay, in that line. And here is another button, and in this time it's disabled because we are in main function, the outermost function, and we can step out from our function, and it's finish. Okay, it's just like finish in Gdb. And another button, if you check that and active that, Gdb will stepping and go ahead in your code instruction by instruction. Okay, when you active that, Gdb will open your disassembly file. Okay, because when you active that, you can go ahead in your code instruction by instruction, not line by line. Okay, here is my disassembly, and in Eclipse you can easily see your disassembly in a beautiful way. Okay, your C code and its assembly. Okay, it's assembly code. Okay, for your C code, and you can see your registers so easily in register. Okay, in register window here. Okay, here is my core register. Okay, my core register, not my peripheral registers, the registers in my core. Okay, or you can see here your local variable, but I don't have local variable in main. Okay, here is my registers and variable. Okay, you can see your registers, you can see your breakpoints. For example, if I want to add a breakpoint to line 9, I can double click on this green bar ahead of in the first of line 9 and add a breakpoint, and you can see here is my breakpoint is added, main.c and line 9. Okay, so let's do next in Eclipse. Press on a step over or F6 to next. Okay, now let's press that. It has some problem. Okay, let's do in this with this button you can restart your code and go to your main function, first line in your project. Okay, restart that. Another time I am in line 6. If I press in a step over, Gdb will go to next line. Sorry, it has some problem. Let's terminate my debug and another time run that. If you want to close debug and terminate that, click in this red square, and if you want to back to previous layout, here click on this perspective. Okay, here is some perspective. What's perspective? You can study about perspective and create some perspective here, the layout of your software. Okay, here another time click on debug button to start debugging. Okay, switch to debug perspective, and here another time I am in the main function. Press next. Okay, I'm in line 7. Another time press next. I'm in line 8. Okay, and let's just see. As you can see, my green LED is off. Okay, my green LED is off. But if another time press next in the line 8, I can turn on my LED. Press next. No. if I see my board, my green LED is on. Okay, here my green LED is on, and I can do my debugging in Gdb. So easy. Okay, I can do my debugging in Gdb so easy. Okay, so another time, reset your debug and press step into. Okay, now I'm in right register. Another time, press step into. Another time, step into SRT function. Press to step return or finish in Gdb, back to upper function and back to main function. I'm in line 7. If I press on resume is continue. Okay, resume is continue, and run your code until next breakpoint. Press resume. I am in line 9. Okay, I am in line 9. Another time, reset. I'm in line 6. Press resume. I'm in line 9. Okay, I can add breakpoint to my project, and I can easily debug my project, and I can see the change in my registers with the register window. Okay, and it can see the change in registers. Okay, we will do a lot of we will have a lot of work with these registers, because we want to do some assembly programming from next part. Okay, from next part I wanted to start to talk about ARM architecture and assembly program. So I will talk about registers and assembly programming from next part. Okay, another time, reset your project and you can see your disassembly code. Okay, so let's terminate debug. And go to coding perspective, close console. Here is my project. I've done some configurations for compiling and debugging, but another time let's go to run and run configuration. Okay, and let's wait to open. Okay, here in my configuration for PyOCD there is a tab, SVD path. What is SVD? SVD stands for system view description. What is system view description? SVD file. SVD file is a file that you can find that in your chip manufacturer website from your chip, and it gives you a lot of information about your peripheral registers. Okay, we saw that I can see my core registers in Gdb and debugging in Eclipse in register window, and I can see my register from my peripherals, for example from my GPIO, analog to digital converting, and all of my peripherals in my chip, with adding SVD file to my project. So how can I find SVD file? For example, for my chip STM32F746, open to your chip manufacturer website, and in this website, wait to open. Please wait. Okay, here in CAD resource tab, I have system view description. Okay, you can download for your chip here, system view description. After downloading, I have my system view description here in download, and here, okay, STM32F7SW. If you open that, you have some file for different types of microcontroller in F7 family. Okay, here is for my microcontroller F746. Let's do copy that in my workspace. Copy in your workspace you have in your project directory, and let's do add to my project. Okay, go to Eclipse workspace, Eclipse workspace in your project directory, and here svd file. Open that, apply and close. Let's do another time debug my project. Click on debug button, and wait to debug runs. Okay, close console. I'm in line 6, but here open peripheral. Okay, peripheral tab in this Windows. Okay, and you have a lot of options for your peripherals in your, for example, ADC, DAC for your debug, DCMI for Ethernet, for your GPIOs and other. Okay, so how can I see the content of my registers, my peripheral register? First, I need to see, for example, the content of RCC AHB1ENR, the register that I program that in this line. It's the address of my register, RCC AHB1ENR, and this register is from GPIO modder and GPIO ODR. Okay, so check RCC in the list. Where is RCC? Here. Check RCC. Let's do first minimize that and check GPIOI. Those peripheral that let's do, okay. Those peripherals RCC and GPIO that I've programmed in my project. Okay, here for RCC and here for modder and ODR. Okay, so when you check all of those peripherals that you need, open memory for your debugging. Where is memory? Go to Window, Show View and Memory. Okay, memory, and let's do that. Okay, in this time you can see I've added RCC and GPIO, and I can see, for example, the register of RCC. Okay, here the register of RCC. For example, AHB1ENR. Okay, one of register that I've programmed in my project. Okay, or for example for GPIO, modder and ODR. Okay, so if I press next, I will write this value in this register AHB1ENR. Let's to see the AHB1ENR here. Okay, here is AHB1ENR, and I want to enable GPIO-I. Okay, if I run line 6, I will write a 1 in this bit. Let's do run. AHB1ENR. I write, okay, here I write 1, as you can see, in this bit. Okay, and if I run line 7, I will write this value in modder. Okay, in modder. Let's open modder, and another time press next. I write the value in this register. Okay, and in the next next line, I will write this value in ODR. Okay, in ODR register. Let's another time press next. Okay, in this way you can easily inspect your peripheral registers with svd file. So you can find your specific svd file from your chip and add it to your debug configuration in svd path tab. Okay, and in this way you can add your register to memory here, RCC and GPIO, and after that see the content of your registers. Okay, it's so easy. You can do all of these works in terminal, but in terminal it's much harder because you should write all of your command and type of all of your command. But in this way, in Eclipse, you can do all of your works in a graphical environment. Okay, it's so easier. So it's enough for today. And since next and from next part, I will start to talking about ARM architecture, computer architecture, and ARM assembly programming. Okay, and we dive to our professional business, do some assembly programming, because we need assembly programming and we need to know about computer architecture and ARM architecture, because we want to write an operating system. Operating system is a system program, is a hard program, and you need a lot of information about your chip to write a real-time operating system or other operating systems. Okay, so from next part I will start to talk about ARM assembly programming. Terminate my debug. Thank you very much to see me, and see you soon in the next part. Thank you very much.